So over the past several chapters, we've talked about a number of different topics. We've talked back in chapter 4 about solutions and the chemistry that occurs in aqueous media. Then we kind of moved through chapter 5 and then went off to chapter 10, where we talked about gases and properties of gases and their corresponding behavior. And then we spent some time talking about molecular structure and bonding and the forces that are involved there. And now what we need to do is return back to some solution chemistry. So solutions and mixtures in liquids, a little bit of phase changes, and talk about the energetics and the processes that go on in liquid media and during phase changes. And we'll find that one central focus of our discussion will be the topic of intermolecular forces. So to begin this topic, let's just briefly return to the 3 states of matter and some of the features of them. So if we take a gas, and let's just look at chlorine gas here, we can note a few common features of gases, and that's that the molecules are far apart from each other, they're randomly oriented, they've got complete freedom of motion, and in the gas phase, the kinetic energy, that is the energy of motion, is much, much higher than any attractive energies between molecules. Remember, we said that gas molecules behave as if they were entirely isolated. They don't really have interactions with their neighbors. If we move to the liquid phase, though, now this is bromine, so we're still in the halogen column. We've just moved down 1 row. Bromine, in the liquid phase, well, molecules are now closely packed together. Unlike the gas, where most of the volume is just empty space, in the liquid now, essentially all of the volume is occupied by the molecules, and the molecules are closely packed together. They're still randomly oriented and moving free, and mostly moving freely. And in this case, though, the kinetic energy, or their energy of motion, is now approximately equal, or at least in the same scale, as the energy of attractions between molecules. And then finally, if we move down the halogen column 1 more, we now get to iodine. And iodine turns out to be a solid. In the solid form, the molecules are closely packed. Now there's very, very little empty space, and they are now packed in an ordered array in a crystalline solid. So there's structure to the way the molecules are arranged. They have essentially no freedom of motion. They're essentially stuck in their particular position. Now, even in the solid form, molecules can vibrate, but that's essentially all the freedom of motion that they have. They can't reorient themselves, at least not very quickly in the solid phase. And now their kinetic energy, which is the energy of motion, is much, much less than the energy of attraction between molecules. So what we'll notice if we look between gas, liquid, and solid, what we see is that we are increasing the level of intermolecular attractions, that is, attractions or energies between molecules. In the gas phase, we have essentially none. In the liquid, we definitely have a lot more, and then in the solid, those attractions dominate. So we'll carry this discussion then forward when we talk about and investigate some of the various types of intermolecular attractions. While we're talking about forces, we really should note that there's actually 2 types of forces when we're talking about molecules. And first, there are intramolecular forces. That means within the molecule. Those are simply the bonds. That's what holds the molecules together, those forces. However, what we'll talk about in this chapter are the intermolecular forces. Those are primarily electrostatic attractions or repulsions between molecules. Now, I say electrostatic, that means that they are based off of full or partial charges, where opposite charges attract each other and like charges repel each other. Now, it's important to note that intramolecular forces, that is bonds, are much, much stronger than intermolecular forces. So it's important to have that distinction there. And we can show that a little bit more clearly if we compare the bonding forces with the intermolecular forces. So here on the left, we have the two primary types of bonding. We've left off metallic bonding. We don't talk about it very much, but the ones we're more familiar with, ionic bonding and covalent bonding, we can see their ionic bonding is very strong. Covalent bonding can range, but is generally pretty strong. And we see some energy values associated with these, somewhere in the range of, say, 150 up to maybe 600 kilojoules per mole. On the other hand, intermolecular forces, even the strongest intermolecular forces, which are ion dipole forces, these are only of moderate strength, somewhere in the 10 to 50 kilojoule per mole range. So we're only talking about maybe 10% of a covalent bond here for the strongest intermolecular force. We also have hydrogen bonding, dipole-dipole forces, and dispersion forces, and those kind of vary in their strength. We'll go through each of those in more detail. Now, while we're talking about intermolecular forces, you may wonder, well, what's really the big deal in between those? Or what's the big deal talking about intermolecular forces? How would we even measure the strength or relative strength of intermolecular forces? There's a number of different ways we can measure intermolecular forces, but there is at least one really useful metric, and that is the boiling point. Boiling point itself is a really good measure of intermolecular forces. We're not talking about intramolecular forces here. Remember, the boiling point is the point at which we're doing a phase change between liquid and gas. And so all we're overcoming when we undergo the boiling process is we're overcoming the intermolecular forces between molecules to then separate those molecules into the gas phase where they behave independently. And so boiling point is a really good measure for the strength of intermolecular forces. And the stronger the intermolecular forces, the higher the boiling point. So as we go through these intermolecular forces in the next couple of videos, we'll kind of illustrate this and reference it back to boiling point in many cases.